Good morning from Berlin. My name's Stuart Smith. About this time last year I was in Helsinki with you and I gave a lecture and I got to know Helsinki a little bit and we had some very good conversations. I really enjoyed being with you. Of course, 1 year on things are rather different and we're getting used to this new format and this new way of living, and we're online. So that you don't have to listen to me for 45 minutes, I'm going to try and break it up a bit, put some of the video content and the slides in between. I hope you find the lecture interesting and engaging, and in 45 minutes time we can have, I hope, a good conversation live and share some ideas and thoughts around the topic. So I'll see you in 45 minutes. Thank you. So thank you for the invitation to talk again. The topic today is around tall buildings and the challenges of tall building design, and I want to focus on what we can do to find a better way to design our tall buildings in the future. So at the beginning of my career as a young structural engineer, I worried about how it was clear to me that our resources were finite. And I couldn't see a way that we could carry on extracting resources and building buildings when clearly our resources were finite. And I spent a long time thinking about it, something like 30 years ago now, and never really found solutions that I was happy with. But for a long time that didn't seem to be such a big problem. Things just carried on as they were. But more recently, we do see the problems. In construction, for example, we see a shortage of sand, a basic construction material for making concrete. With concrete, we see a huge carbon impact from cement, and the energy that it takes to make and deliver our materials to site, to build our buildings, is enormous. And in the context of climate change, this is now a major problem that we have to deal with. And we have to deal with it very quickly, we know that. So it's taken a long time to get to the point where we really see these problems and understand them, and also have the solutions for how to deal with them. Because I feel like today we do have the solutions to deal with this, but we need to do it very quickly. So today I'd like to talk about tall buildings in that context, and I'm going to come at it, I think, I only really can come at it from a European perspective. Whilst I've got lots of experience of working in many parts of the world, I think we have a very unique opportunity in Europe. Because of the way we are, because of the cities that we have, because of the way the cities are run and administered, I think there are huge incentives for us and huge opportunities to find a better way and a different way for the way we build and construct, and in particular for tall buildings. So if we look at our cities, we know that they consume enormous proportions of resource. We're urbanising at a massive scale, so we have a projection of 2/3 of our population, something like 6 billion people, will live in cities by 2050. And the consumption of our resources is something like 75% from the cities. And that's also responsible for 50% of the waste we generate. And on top of that, about 60 to 80% of our greenhouse gases. And a big part of our cities are the tall buildings that we build. So there's a huge incentive for us to get that part of it right. And I also find it really fascinating, a fact that I recently discovered, thinking about how many tall buildings have been demolished. So, tall buildings over 150 metres. How many of those do you think have been demolished, ever? Well, it's less than 10. And for me, that's a real surprise. There are something like 1,300 tall buildings over 200 metres tall. To my knowledge, I don't think we've demolished any of those buildings over 200 metres. There is one that was under consideration in New York. So when we build these buildings, they stay for a very, very long time. we tend to keep them. And so it's really essential that we get them right. And I also want to talk about that. How do we get them right and how do we keep them for a long time? And there are many components to that in the design and the construction of our buildings. I also see that we have huge incentives now to do better. We have in Europe the EU Green Deal. We have cities like Copenhagen and Amsterdam that are making pledges to reach carbon neutral by 2050, and that's what we need to do. And I feel certain that more cities will follow, more momentum will grow. The next 10 years is really important in this journey. So we have the EU Green Deal, we have cities and city mayors aware of the problems, and we have a population that wants to change. We also see in Arup lots of opportunities coming from the green economy, from green investments. People no longer want to invest in projects that they can see are just business as usual. They want more than that. They want a green future, and they're also concerned about the value of their investments in the future. So one of the major drivers that we see, and I learned this term recently, and I found it really, for me, just illuminated the problem. It's the concept of stranding. So stranding, I come from a seaside town, Southend-on-Sea, and it has a very high tide range of about 6 metres. When the tide goes out, the boats sit on the foreshore and they lean over. They're in effect stranded. Imagine that happening to our buildings and our assets. They're no longer valuable, they've been left behind, they consume too much energy, they're in effect stranded. Your asset or your investment is stranded. So we need to make changes today because this is happening so quickly, so that in the future we still have valuable buildings, we still have buildings we want to use, so they aren't in effect stranded. So I think you put all that together, there's a huge incentive to do things differently. We do know how to do it, and that's what I want to talk about today. So our tall buildings are going to be there for a long time, which means we have to get the environment in which they work right. And that's a topic that I found really interesting through the development of my career. I think back 10, 15 years, and we were only just beginning to develop the tools to study the environment around our buildings. We were exploring city physics on a bigger scale and really understanding the impacts of placing a tall building in a city. So there's an impact on the wind environment around the building, an impact on the light and the shade. How could you make sure that the outdoor spaces around the building were useful? And even how could you make sure that the outdoor spaces up the building were also going to be useful? So we did a big master plan at White City in London with OMA, and the proposal was basically to try and get as much density onto the site as possible whilst maintaining environmental quality. And I think when we think about sustainability, we must also think about land use as a resource that we can't just use endlessly. By making our cities more dense, we're avoiding them growing more wide. So it's really crucial that when we have well-connected inner city transport nodes, that we make the most of those locations in terms of density of development. But we must do that not at the cost of the environment. So it's increasingly important as we try to build more dense around these transport nodes that we really understand what we're doing. So we had White City, we studied with a whole series of analysis models, and we were trying to create one model that would allow us to study all of these factors in one so that we could determine relationships. Jump forward some years, and we're now finding that we can not only study versions of one development, but we can allow the computer to start to find the best solution. So we can program parameters into a computer. So one of our parameters can be environmental quality in terms of sound, acoustics, if we're trying to build it inside the city, then we'll have noise from traffic, from railways and so on. In terms of light, we can study that, and in terms of wind, so we can put all of that together and we can find the optimum solution. Recently our team in Amsterdam have developed models where they can study iteratively thousands and thousands of solutions very, very quickly just by writing in the parameters. And we won a competition, Smackler's Park, where the purpose of the project was really to try and find the best environment for the densest development, and we were successful with that. So the opportunities there have developed enormously. That means we can make much better use of our land. We're not completely there. We still find, and we have to be very careful when we design tall buildings, the wind environment is very, very sensitive to the shapes of the building. And I remember a development that I worked on in London, near London Bridge, where we studied the wind environment. We went into the wind tunnel, and then very small adjustments of the shape and form of the building throughout the height of the building made quite a big difference to the wind environment at the base of the building. And we recently also found this working in Helsinki on Trigoni, where we studied the environment at the beginning of the project, and it requires a lot of work as you go through the project to deliver that same quality. So, essential to keep the environmental quality of the urban realm when we're designing our tall buildings. So now I want to talk about optimisation and the role that plays. Because one thing that's clear is that we do have finite resources, so we need to minimise the amount we use. And that makes sense in any model. And we've explored this topic enormously in the development of computer power and the way that we work on our projects. So I go back 20 years or more now to when I first started working in China, and we were working on CCTV. And I met a young colleague, and I was much younger then as well, Peng Lu, who now runs our Beijing office. And together with Beijing and London, we worked together on CCTV. And we developed models, computer models and analysis models, where we could optimise the steel in CCTV, and we could also explore the pattern for the geometry and the architecture of the building. I jump forward now 20 years, and Peng and his team in Beijing have just delivered a project called China Zun, which is an astonishing project. It's a super tall tower in Beijing. They've used all of the power of optimisation and parametric design to find an optimum solution, cycling through thousands and thousands of different options, finding the best floor plate for steel weight ratios, adjusting the shapes, changing the geometry, very small changes making quite big changes to how much steel is used in the building. So there we've had great success. That project is just completed, and there's a lot in the press around the project. And that kind of work now is feeding back into more routine projects. We're now setting up parametric models where we can change and adjust parameters to find the best solutions in terms of material weights and so on. The next part of that, I think, is allowing the computer to start finding the solutions for us. That starts to suggest artificial intelligence plays a role in this. I've been looking recently at the work another friend and contact of mine, Philip Block, who runs the Block Research Institute at ETH in Zurich. And they've been exploring with parametric optimization and 3D printing of floor plates that have material just where you need it. At the moment we tend to make our floor plates as flat slabs or beams and slabs. It's a very simple way to build, but if we could just take out the material we don't need, we could use substantially less material in our buildings. Something like 50% less would be possible in terms of the structural performance. I think if you put that together with some of the other things we're talking about here, if you add that idea to modular component-based design, then you can optimize by component. You don't have to bring the materials to site in the same way. In situ concrete tends to suggest that you're going to build flat slabs. If you can build components in the factory, then you can use parametric design and digital fabrication to make the pieces, assemble them off-site in larger components, bring them to site and assemble them as one. I've also had some interesting conversations with a construction company in London called Mace, and with a construction company in Australia called Hickory Building Systems. And they've been partnering together to develop ideas around how you could build from more component-based design. And I find their ideas really interesting. About 2 or 3 years ago, working on a project in Stockholm with Oscar Properties, Gaslocken, we were exploring how could we build that in a similar way. And we went to visit a project called East Village in London at the Olympic site. This is a residential tower, and Mace were responsible for the construction. What they did was, they built a 5-storey factory in steel frame on the floor, and within that they built the building. And as they got taller, they jacked the factory up, so it travelled up the building as they built within that enclosure. So that was weatherproof. It allowed them to build in a factory environment. That meant that they had some overhead cranes in this factory environment, and they could bring the pieces inside and then locate them almost as if they were building in a factory. Once you do that, then you can get all of the other benefits. And I can also see the possibility then, if you have a component-based design that's delivered to a factory environment, you can start to imagine robotic construction. You can imagine GPS sensors, you can have pieces that can then be located. We're not there yet, but I can see that in the future through this system. In Australia, Hickory have gone another step further, perhaps in terms of modular design. They've cut the frame up into pieces in terms of the design. They've built the pieces off-site and they've attached the facades to them. And then they bring them to site and assemble them. So it's more of an assembly process, not of the whole volumetric construction, but of smaller volumetric pieces. That means that they can build to very high tolerances. It also means that the construction's much quieter. It's a different thing if you're assembling pieces as opposed to on-site with construction traffic, delivering materials, often wet materials, and have a big on-site process. If you're delivering components and fixing them together, it's much quieter. So Hickory in Melbourne have agreed with the city that they can deliver their pieces overnight using electric cranes, so they can put them in, and it's a very quiet process. That takes construction traffic off of the roads. It means the construction's much more accurate, much quieter. I can't really see any disadvantages to this. I also imagine that if you've got these very high tolerance construction frames in terms of the structure, that all of the other components then can be manufactured digitally and brought to site and assembled. So traditionally the things that fill our buildings in terms of kitchens, bathrooms, partitions for offices, all of those other components, when we bring them to site, we've often got a problem between the tolerances of an in situ on-site process and the tolerances from a factory manufacture process. by doing both of them the same way, we have much better fit between all of the components. What that means is we can generate less waste, because we don't need to allow for tolerances. So we don't need to make, say, the worktop of a kitchen doesn't need to be bigger than it actually needs to be, because you don't bring it to site, put it in position, cut the bit off you don't need, to actually fit it into the space that's there. If you've gone through a digital process and an off-site manufacturing process, then your tolerances through the whole process are much better. So that has quite big implications for all of the components of the building if we can design that way. And as I say, I think if you can bring digital optimization and fabrication to the process, then you save materials through that as well. So it's a process of optimization and design that runs right the way through the whole process to save materials and make it better. So let's talk about timber and the role that can play in high-rise construction. There are so many benefits from timber. It's a lightweight material, which means it's easy to transport and erect. It's a renewable source, so we can grow our timber as we need. And it sequesters carbon, so that means it has carbon absorbed within it. So there's some great benefits there, and it's a natural material. People like being around timber. We've been developing the idea around timber in high-rise construction and in our buildings for some time. We have a fantastic example of a really innovative project, H7 or H7 in Münster. This is a project where we removed concrete and replaced it with timber beams, and then kept a concrete floor plate over the top. And this has got great benefits. So it combines two materials in the best way. The concrete provides the acoustic separation, and it also provides the fire protection. And the timber replaces a high carbon material. So there are great benefits in putting them together. We could make the components off-site. So we had timber concrete composite panels made off-site, brought to site and then assembled. Because it's lighter, it also requires lighter foundations. So it's faster to build, it's lighter, it's easier to transport, it uses natural materials, has a much better carbon balance. And we've started to explore using this floor plate system in tall buildings. So recently, we won a competition in Munich working with David Chipperfield Architects. This was a tower. We proposed a timber concrete hybrid, and that's now been adopted and is being used in a high-rise building. And we're seeing this happen in many places around the world. We're also seeing a lot of incentives from local city administrations to build more in timber. I think probably many of you will know that in Paris, the local mayor has said that they want 50% of the public buildings to be built in timber. In Amsterdam, our team working on a project were incentivised to build more if we built a sustainable building in timber. So we proposed a timber frame with a timber core for a building that was about 75 metres tall. It's Hout, and it's under construction now, so we've seen it all the way through and it's on site. Along the way, we've solved lots of technical challenges that will inform us in the future. So it's very difficult to deal with dynamics in timber because it's lightweight, much lower stiffness than steel and concrete, so much more susceptible to wind vibrations. So to solve that problem, we've introduced a concrete core and attached the timber to the concrete core. And that's a solution that's being used for many of our projects where we're combining timber with concrete. And I think there's a really good opportunity there to balance high carbon with low carbon materials and to get the appropriate materials in the right place in the building. And that would have then allowed us to use more timber in our construction projects. So that was one issue. Fire, of course, is another issue, and there's been lots of work done on fire in tall buildings and in timber buildings, and that knowledge is now being brought into projects. But I also have some concerns if we use timber for all of our projects, because as we saw with sand earlier on in our conversation, sand as a construction material has suddenly become in short supply. And that's simply because with such a large population, if we rely on one solution for all of our topics, then very quickly we use up all of the resources. And on top of that, timber requires land. So there are issues around how we use land. So we have to be very careful that we use timber in a sustainable way. And I think the idea of mixing timber and concrete is a good way forward, is a good way to approach that issue. So more timber in high-rise construction is definitely something that we see in the future. We've been working with the Council of Tall Buildings and Urban Habitat here in Berlin. My colleague Carsten Hein is leading a working group to study the issues and develop into the future how we adopt and how we use timber in high-rise buildings, what are the limits and what we should do and what we shouldn't do. So this is emerging, and I see more of this happening in the next 10 years. And finally, one of the really positive benefits we find with timber, if you put together the advantages with timber concrete composites, then what we find is that they're not more expensive than the traditional solution. Because you've got the benefits of fast construction and lighter weight, it means that you save money in terms of the overhead costs of construction. There's a little bit more money in the material costs, but the two things together balance out. And so it's almost like what's not to like. You're getting more sustainable buildings, and you're getting them at the same cost as more conventional solutions. And in Germany in particular, we've seen a massive rise in the supply chain, so it's much easier now to design and procure these buildings. So let's talk about existing buildings. Since our tall buildings are kept for a very long time, we have to figure out strategies for how we're going to use and reuse them. And this could be a big issue in the future, with so many tall buildings in so many of our cities, many of them social residential housing. So how do we solve that problem? Well, I was lucky enough to listen to Anne Lacaton last year in Cairo, talking about a project in Paris where an existing social housing block, which has had many problems in terms of what to do with the building, what to do with the community that lived in the building, and how to address what basically was a building that was performing very badly with poor thermal envelope, bad facade, bad conditions within the building, leakage of the facade, lots of different issues. And the plan was to empty the building, demolish it and rebuild. Lacaton and Vassal came along and found a way to keep the building in place, refurbish it and improve it and leave it better and fit for the future. And I think the project is a fantastic example of what we can do when we challenge ourselves. Lacaton and Vassal have particular expertise in how to deal with existing buildings, but this project I think is a fantastic example. So what they did was, they extended the front of the building by one bay, and in that bay they created winter gardens and terraces that would connect residents. It was very skillfully done on site. This additional bay was built outside of the building, and then once it was in place, it was used as the construction deck to access each of the apartments individually, to connect the two, the existing building and the new bay built in front. And I'll give you details of the lecture by Anne Lacaton. It was fantastic. But the idea was then that the residents would move their TV sets, their curtains, everything they'd move 2 metres back from the facade. They'd put in a temporary barrier, construction firm. They'd cut the facade out and connect it to the outdoors, to the new bay, and then replace everything. That kept the residents in place through the construction process. It kept the community in place. When we find these existing buildings which are performing badly, we also find though that there's a community there that wants to stay together. So this was a huge saving in terms of carbon and materials. It was a huge benefit to the society and the community that lived there, and it was cheaper than demolishing and rebuilding. So if we want to have a low carbon future, we have to find intelligent ways of dealing with existing buildings. And this was one really good example that I always use, and I've remembered it for a long time. Another really good example, we're looking at opportunities for how to reclad existing buildings, give them a longer life. We have a commercial building in London called Triton Square, which actually wasn't that old. Commercial buildings can have a very quick turnover in terms of their market value. And we're quite often seeing buildings in our cities demolished after only 20 or 30 years of use. We can't really carry on doing that in the future. And at Triton Square, we looked at a rebuild scheme, but decided that really we could reuse the building. And we took the facade off of the building, took it to a factory close by, refurbished it and put it back onto the building. What probably many of us don't realise is there's something like 25% of the carbon in a construction is in the facade, in the glass and the aluminium sections. So it's really important that we find ways to use and reuse our facade materials. And Triton Square is a really good example of how to do that. And we can look back at other examples. So in New York City, I found it really interesting to learn that the Empire State Building has had the facade replaced or the windows replaced more than once. The last iteration, all of the windows were taken out, the glass was cleaned and recoated, the frames were stripped down and rebuilt, and the windows replaced. There's something like 6,500 windows in the Empire State Building. that's clearly a historic building that we wouldn't ever imagine demolishing. But that's the way we need to think about our buildings in the future, whether they're historic or whether they're social housing that's been made in poor construction. We need to find strategies to use and reuse the materials in the buildings, keep the communities in place, but still improve the performance of the buildings so they can meet modern standards, but not use lots of resources. So let's talk about concrete. How can we design better concrete structures in the future? There's a real issue with concrete at the end of life. How do you reuse concrete from demolished buildings? And there's a real issue with cement, and how you make cement without carbon. Now, I've been lucky enough to work on a number of high-rise concrete buildings, Beirut Terraces with Herzog & de Meuron, and BBVA headquarters in Madrid, again with Herzog & de Meuron. And they're both projects that I'm really proud of. Now, how would we do these projects differently? How would we do them in a concrete sense? How would we reduce the carbon and make them more sustainable? So there's a journey to take with the materials industry and with the supply chain here. And we're starting to see some solutions come into practice. So one example, carbon cure. Carbon cure takes waste carbon from other industrial processes and it puts it into the concrete mix on site and replaces water. So it uses carbon to cure the concrete. The carbon is then captured in the concrete mix and never will be released again. So that's a fantastic opportunity, I think. If we can make that work, we could repeat that on many projects. Well, one of the problems with bringing that technology into construction is that the concrete then cures very quickly. So typically concrete would take 28 days to gain its strength on site. That means it's very workable, which means you've got plenty of time to get it into the right place. If you're arriving at a construction site and there's traffic, no problem with waiting a bit longer. Generally, concrete is appreciated by the construction industry because it's a very easy to use material. So carbon cure puts the carbon into the concrete on site and that solves that problem. It then takes 1 day to cure, so it makes it very fast construction. It's also possible to use that technology off-site, so making precast pieces. So if we can have modular and precast construction, we can start to build in a factory environment. We could start to take more use from some of these emerging technologies. Another area where we want to improve, when we demolish our buildings, we take the concrete material and we use it as landfill or we use it as road base. It's downcycling the aggregates. The industry now is looking at reusing this demolished material to replace aggregates in concrete mixes. So for the first time we can imagine this circular economy of concrete structures where we're reusing materials. There's also other opportunities. Well, at the moment we're using waste materials like fly ash and ground blast furnace slag to replace cement in our concrete mixes, and we're driving the cement content to lower levels with these replacement materials. LafargeHolcim now have a product in Germany called EcoPact concrete, where the carbon content of that mix is offset so that the net impact is carbon neutral. So those are opportunities that come through our construction processes and our materials processes and our supply chain that we could make much more use of in the future. Another component of this is to use carbon capture and storage on site where our cement is manufactured. Now, that's something to explore in the future, but we have many things which we can use now which will help us develop lower carbon cement and therefore concrete in our building. Okay, thank you for listening this far. I want to try and just bring together some of the topics and bring it to a summary. There are, for me, really three parts to this. We've got to decarbonise our materials and our supply chain. And we've got to design and develop our buildings and projects in a circular way. We've got to design things so that we're not taking resources, making things and then demolishing them. We've got to change that to a circular model. And the third part of it is that we've got to do it all really quickly. But I think that we do really have a moment and we do really have the opportunity to do that. We just have to really get on with it. We've got 10 years to solve the climate problem. And the projects that we're designing now will very quickly become the projects of tomorrow. Things are changing so quickly we can't afford to carry on the way we have done in the past. And throughout my career I've seen lots of change. I've seen lots of change in the way we design projects and the way we do things. And I'm optimistic now that we can change things very quickly and make a difference and find for our buildings and our built environment a better way. Thank you.